Hi, I'm Mitch, and this is my third video in a series about magnification with a simple converging lens. You may recall in the previous video I demonstrated that if an object distance is less than the focal length, the rays will diverge on the back side of the lens. But if you trace them backwards, they will converge on the front side, behind the object, making it apparent to an observer on the back side that this is where the rays originated from. The resulting image is magnified and upright, and because the light rays do not actually travel backwards and converge here, we call it a virtual image and depict it with dashed lines. Virtual images have some properties that make them useful in lens assemblies, and in this video I'll contrast those to the properties of real images. Now, I've depicted the position of the observer to be here, but if we move the viewing position as depicted here, the observer can still see a focused version of the image, but the perspective of the image will change. Now, instead of a perspective centered at the top of the object, the perspective is shifted to a slightly lower spot on the object. So a virtual image can be viewed from any location behind the lens, but the perspective of the object will change. Let's compare that to a real image, which must be viewed at the image plane. If the observer is in front of or behind the image plane, the light rays will not be converged and the image will be blurry. So that implies the second property of a virtual image, which is that the sensor location is not the image location. In fact, it can't be. If the sensor was here, it couldn't sense the image. Whereas for a real image, the sensor location must be at the image location. This is kind of restating the first property that I mentioned on the previous page. I'd also like to point out here that I've switched from the word observer to the word sensor, and I've replaced my eyeball with a camera sensor array to make the point that both those ways of sensing the image are interchangeable with respect to these concepts. Now note that in this virtual image, the object is pretty close to the lens. If we move the object away from the lens and towards the focal plane, we increase magnification. Recall that to increase magnification of a real image, we also needed to move closer to the focal plane, but that also required moving closer to the lens. So the third property of virtual images is that greater magnification is achieved closer to the focal point, which is further from the lens. And then, of course, if you cross over the focal point, you don't have a virtual image anymore. You transition to a real image. Now I'd like to take a minute to talk about differences in how you'd actually view the image. I've already said that a camera sensor array is essentially interchangeable with your eyeball, but the full camera is not necessarily interchangeable because it also includes one or more lenses already installed. So if you were trying to sense a real image with your eyeball, you'd probably have some free optic like a magnifying glass, and you just use trial and error to place the object and your head in the correct combination of distances from the lens that produces the sharpest upside down image, which is really difficult for a real image. Usually when you're looking through a magnifying glass, what you're seeing is a virtual image, and it's right side up. In a camera, the lens would likely be in a zoom assembly, which you could twist to adjust the image distance to focus on an object that's probably more or less fixed at a certain object distance. Another way to image the object is to project it. You need to be able to shine a light through a semi-transparent object and then place a screen, wall, or any other flat surface at the image plane. So a real image can be both sensed and projected. But projection requires that the rays converge again on the back side of the lens. So while the setup for sensing a virtual image is basically the same as for a real image, any attempt to project an object that is between the lens and focal point will result in a blurry mess. So a virtual image can be sensed but not projected. To finish off this list, let's remember that every virtual image I've shown has been upright with an object between the lens and focal point such that the object distance is greater than 0 but less than the focal length. Whereas every real image I've shown has been inverted with the object between the focal plane and infinity. So it's just beyond the focal plane. Finally, this table summarizes the properties I've just discussed.